Hey guys, this is Ayushi from Edureka, and in today's session we would be discussing an algorithm that helps us analyze the past trends and lets us forecast what is to unfold next. So this algorithm is time series analysis. Now let's quickly jump on to our agenda and let's see what all we're going to cover in today's training. So we'll start off this session by understanding why do we need time series analysis, and then we'll understand what exactly it is. Now once we're clear with time series, we'll then see the different components that we need to take care while we apply time series. Then we'll also discuss when should you not use time series analysis or what are the cases when you should not apply time series analysis. Moving ahead in the session, we also discuss what is stationarity or what are the tests that are used to perform to check the stationarity of the data. Next, we'll be discussing the ARIMA model. Now, ARIMA model is one of the best model that has been used in time series. So we'll have a discussion on that and we'll finally go ahead with the demo part wherein I'll implement all these things and help you guys to forecast the future as well. So I hope you guys are clear with the agenda. So kindly drop me a quick confirmation or you can just write it down in your chat box so that I can proceed. Alright, Monisha says a yes. Okay, Swati gave me a thumbs up. Naman, Shivani. Alright, since you guys are clear, so let's begin with the very first topic, that is why should you use time series analysis? So first of all, in time series analysis, you just have one variable, that is time. Now you must have seen there is a lot of algorithms present. Then why do we need one more algorithm, that is time series? So let me explain you this with an example. Now let's take an example of a supervised learning. So under supervised learning, we have linear regression or logistic. So there we have an independent variable and we have a dependent variable. So there what we do, we deduce a function or you can say a mapping function of how one variable is related to another. And then we can go ahead with the analysis part. But in time series analysis, you just have one variable, that is time. So for example, you own a coffee shop and it's quite a successful coffee shop in the town. So what do? You try to see how many number of cups of coffee you sell every month. For that, what you will do, you'll add up all the sales of your coffee. Now, let's say you started this coffee shop in the first month, that is the January. So what you'll do, you'll record the data month wise and then you'll sum it up. So you will have all the data till the present month. But what if you want to know the sales the next month or the next year? Now imagine guys, you just have one variable, that is sales, and you need to predict that variable in accordance with time. So in such cases where you just have time and you need to predict the other variable, you need time series analysis. Now we know why do we need time series analysis. Let's move ahead and understand what exactly time series is. So time series is a set of observations or you can say data points which are taken at a specified time. Now over here at your x-axis you have the time and on the y-axis you have the magnitude of the data. So if you try to plot time series plot on the x-axis, you will always get the time which is divided into equal intervals. So you cannot create a time series if one data point is at week level and other are different. There should be equal interval, let's say a day, a week, a month, a year, a decade, and a century. So that is the constant thing that a time series require. Now let us see the importance of time series analysis. Now first and foremost is business forecasting, because your past defines what is going to happen in future. So let's say you'll be seeing a lot of traders in the Sensex who are trying to predict what will be the price of the stock market tomorrow. So that is nothing but a business forecasting. You also see a lot of retailers who tries to know how many number of goods they are going to sell the next day. So all of this can be achieved with time series analysis. Now this is not just limited to one domain like retail or finance, but it is applicable almost everywhere. Now it is also help us to analyze the past behavior. So here you can analyze in which month did the sales went up or when was the dip. So here you can easily understand your past data. So with every dip and a peak, there is a business reason attached to it. So you can understand this with respect to time. For example, some festival is there and you're selling chocolates. So your sales will increase during a festival. So you need to think about the seasonality part also. Now don't worry guys, we'll be having a complete discussion on seasonality as well. So now coming back, it also helps you to plan the future operations. So you can analyze the past and then you can forecast your future using this algorithm, that is time series analysis. Now apart from all this, you can also evaluate current accomplishment. So this means you can determine which goals you have met in the current scenario. Let's say you have predicted, okay, I'm going to sell around 100 chocolates in a day. But did you actually do that? So all of this can be analyzed using time series analysis. Moving ahead, let us see the different components of time series. Now, most of time series have trend, seasonality, and irregularity associated with them, and some of them do have cyclic patterns also. But it is not compulsory that there has to be pattern present. So let us discuss each one of them in detail. Now, the first is trend. So trend is nothing but a movement to relatively higher or lower values over a long period of time. So when the time series analysis shows a general pattern that is upward, we call it an uptrend. Also, if the trend exhibits a lower pattern, that is down, we call it as a downtrend. And if there was no trend, we call it as a horizontal trend, or you can say a stationary trend. So now let me explain you better with an example. So there is a new township that has been constructed. Okay, and people are going to come and live over there. So what happens? A hardware guy comes up and opens up a shop there. So people who will be coming up will definitely buy stuff from there. Now, once all these houses are settled up or it's been occupied, the need of hardware reduces. So the trend may go down. So let's say the sales were up in the first year, and by another 1 year or maybe in 6 months, it has gone down. So that is the trend, guys. So for some amount of time, selling was high and then it got down. But this is not a pattern. This is something that is happening year on year. But trend is something that happens for some time and then it disappears. Then we have seasonality. So here seasonality is basically upward or downward swings. But this is quite different. It's a repeating pattern within a fixed time period. So for example, Christmas happens every year on 25th December. Let's say you're on the business of chocolates. So every year on year, chocolates are served more and more in the last week of December. Now, this is because Christmas is there, and you will be noticing this across the year. That is from past 2 years, 4 years, 6 years, 10 years, and so on. So, it's a repeating pattern within a fixed time period. While in trend, that is not the case. Now, let me take another example. Let's say ice cream this time. So, ice cream sales will go comparatively higher in summers rather than in winter. So, that is again a seasonality. Then we have irregularity, or it is also called as noise. So these are erratic in nature, or you can say unsystematic. It is also called as residual. So this happens basically for short duration and it is non-repeating. So here let me give you an example. So let's say there is a natural disaster. Let's say there is a flood in your town out of nowhere in 1 year. Now a lot of people are buying medicines and ointment for relief. But after some time, when everything is settled up, the sales of those ointments have gone down. So this is something that no one could have predicted. It's going to happen erratically. You don't know how much number of sales are going to happen. So you cannot foresee about the event that the flood is happening. Okay, so this is some random variation. So this is what irregularity is. Now moving ahead, we have cyclic. So cyclic is basically repeating up and down movements. So this means you can go over more than a year. So they don't have a fixed pattern. So they can happen anytime, let's say in 2 years, then fourth year, then maybe in 6 months. So they keep on repeating and they are much harder to predict. Now moving ahead, let's discuss when not to apply time series analysis. So first of all, you cannot see time series analysis when the values are constant. So let me take the same coffee example over here. So let's say the sales of number of coffee in the previous month were 500. Then this month also the sales number is almost the same, that is 500. Now I wanted to predict the number of sales in the next month. Now, in such cases where the values are constant, as in our case, the number of sales were 500 in the previous month, and then in this month also we have the same number. And now we want to predict it for the next month. So, in such cases where the values are constant, time series cannot be applied. Similarly, if you have values in the form of functions, let's say you have sine of x or cos of x. So for example, in this case you have x value and you can get the value by just putting it in the function. So there is no point of applying time series analysis where you can calculate the values by just using a function. Now you can apply time series to these as well. But again, there is no point of applying it if you have a formula before that or the values are just constant. So these are the cases when you should not apply time series. Moving ahead, let us see what is stationarity. So no matter what guys, how much you try to avoid the stationarity part, it will always be there in time series. So here time series requires the data to be stationary. So any kind of statistical model that you apply on time series, the data should be stationary. So let's understand what exactly it is. Now most of the models work on the assumption that time series is stationary. Now if the time series has a particular behavior over time, there is a very high probability that it will follow the same in the future. Also, the theories and formulas that are related to stationary series are more mature and easier to implement as compared to a non-stationary series. Now, there are two major reasons behind the non-stationary of a time series. So, first is trend, which is basically the varying mean over time. Secondly, we have seasonality. So, this is the variation of a specific time frame. But did you guys get the answer to this question? What exactly is stationary or how exactly stationarity is defined? So, stationarity basically has a very strict criteria. The first one is it should have a constant mean. Now here the mean should be constant according to the time. Secondly, we have constant variance. So again, variance should be equal at different time intervals. And thirdly, we have autocovariance that does not depend on time. So for those of you who don't know what mean is, I'll not go into the details, but I'll just explain you in a nutshell. So mean is basically the average. Then variance is just the distance from the mean. So each point's distance from the mean should be equal. And then we have autocovariance that should not depend on time, or it should be equal as well. So for example, let's say you're standing at time t, okay? And your previous time period was t minus 1 or t minus 2. Let's say there are previous two time periods. So the values at t minus 2 or t minus 1, t, they should not have any kind of correlation between them, which is basically dependent on your time period. So that is nothing but autocovariance. So when these three conditions are met, then we can say our series is stationary and then we can apply time series analysis over it. Now to check the stationarity in Python, we have two popular tests. Now first is ruling statistics and the second is ADCF, or you can say augmented Dickey-Fuller test. Now in ruling statistics, we can plot the moving average, or you can say moving variance, and see if it varies with time. Now by moving average or variance, I mean that any instance t will take the average or variance of a time window. Let's say if you want to know for the last year, that is for last 12 months or anything. And also guys, this is more of a visual technique. So you cannot deploy this kind of stuff on production, but it is quite useful for the POC purpose. Then we have ADCF, or you can say augmented Dickey-Fuller test in the world of data science. So Dickey-Fuller test, which is another statistical test for checking stationarity. Now here you have the null hypothesis, which is time series is non-stationary. And once you perform this test, you'll get a result which comprises of a test statistic and some critical values for different confidence level. Now here it is said that if the test statistic is less than the critical value, we can reject the null hypothesis and say that the series is stationary. So don't worry guys, I'll be explaining this again when we go to our demo part. But I hope you guys are clear with what exactly is stationary and how you can check the stationarity. Alright, so now let me just move on to my next topic. So now we'll discuss what exactly is ARIMA model. Now ARIMA is one of the best model to work with time series data. So this is basically the combination of two models, that is AR plus MA. And it's quite powerful guys. So once you combine both of these models, you get the ARIMA model. Now your AR model stands for autoregressive part and MA model stands for moving average. So AR is a separate model, MA is a separate model, and what binds it together is the integration part that is indicated by I. So AR is nothing but the correlation between the previous time period to the current. So what does this mean? Now let's take this into consideration that you are standing at a time period t and there are previous time periods like t minus 1, t minus 2, t minus 3. Now if you find any correlation between t minus 3 and t, that is nothing but the autoregressive part. So as I told you earlier that there is always some kind of noise or irregularity attached in a time series. So we need to figure out that noise. In fact, we need to average that out. Now whenever we try to average it out, the crust and drops that are present in that noise smoothen out and we can have average forecast of that noise. You can actually never predict when a next customer is going to come in and buy 100 items at once. So we try to smoothen it up by taking its average. Now, ARIMA model has three parameters. It has P, it has Q, and it has D. So P basically refers to your autoregressive lags, then Q stands for moving average, and D is the order of differentiation. So we have each parameter for each of the models. So if we take the integration by just one order, then the value of D would be 1. If we differentiate it in the order of 2, then we have the value D equals to 2. So that is how we can predict these values P, Q, and D. And each of them has a different method to it. So if you want to predict the value of P, you will be using an PACF graph, that is nothing but a partial autocorrelation graph. Then to predict Q value, we need to plot ACF plot, that is autocorrelation plot. And D, I have already told you, to make data stationary, we use some kind of differentiation. So the order differentiation defines the value D. So I guess enough of theory part. So now let's quickly jump on to the demo and let's see how you can implement all of these things. So now we'll have a look to a demo and we'll forecast the future. So here we have a problem statement where there is an airline which has the data of passengers across months. So here what you need to do, you need to build a forecast to determine how many number of passengers are going to aboard these airlines at the month level in the future. So here we have month, or you can say dates. So here we have dates from 1949 till 1960 and we have the number of passengers traveling per month. So now we have this kind of data and we need to analyze what will be the number of passengers if we have to predict it for next 10 years. So now let me just go to my Jupyter notebook and let us see how my predictions look like. So guys, this is my Jupyter notebook wherein I have the code and we'll be implementing all the things that we have discussed till now. So first of all, we'll be importing all the necessary libraries. So here we have imported NumPy, Then we have imported pandas for data analysis part, and you can say data processing. Then we have imported matplotlib for data visualization, creating plots and all those things. Then in order to implement matplotlib, we have also written percentage matplotlib inline for Jupyter Notebook. So you'll not get a particular plot open in a new window. Everything will be there in your Jupyter Notebook itself. And then I have just defined the size. So now let me just run this. Next, what I've done, I've imported my air passengers data using pandas. So we have a function of read CSV in pandas that is represented with PD. So we have substituted this in a variable data set. And then what we have done, we have just passed those strings in a date time format. So here we have set our data month wise. So using pandas, we have a function to date time. So over here, you can specify a month, and then you can just set this as your index. So here you have index variable as month. Next, what I have done, I have imported date time. And then I have just printed the top 5 values. So now let me just run this. So this is how my data looks like. So I have month as my index, and then I have number of passengers as my second column. So this data I've already showed you in the presentation, wherein I have the data from 1949 till 1960. So I have just printed the head of it. So now let me just print the tail. So let's say I want to know the last 5 data entries. So here we have data till 1960, and we have the number of passengers. Next, what we have done, we have simply plotted a graph between them. So guys, in time series, we have date and we have another variable. So here my other variable is number of air passengers. So here we have date on my x-axis and number of passengers on my y-axis. And then we have simply plot that graph. So now let me just run this. So this is how your data look like. So here if you notice you have a trend. So your next step is to check the stationarity. So I'll give you 10 seconds guys and think whether this data is stationary or not. So just think and give me a reply whether this data is stationary or not. Right, Shivani. So this data is non-stationary. So here you can see the trend is going up. So let's say if you want to calculate the mean at 1951, so here your mean will lie somewhat over here. And let's say if you want to calculate the mean of this year, that is 1960. So here your mean will be somewhere here. So here you can see that you have a upward trend and the mean is not constant. So this tells me your data is not stationary. So now I have told you guys that there are two tests which basically helps you in checking the stationarity of the data. So here we have rolling statistics as well as we have ADCF. So let us go through each one of them. So here we'll be first going to the rolling statistics. So here we have rolling mean and we have rolling standard deviation. So here as you can see we have a window of 12. That is nothing but the window of 12 months. So let's say we have Jan of 1949 and you place the value of Jan 1950 with the value of 1949. So this gives you the rolling mean at yearly level. And you have to do the same with the standard deviation as well. So in Python to calculate mean and standard deviation, you have a function dot mean and you have dot std. So this will automatically calculate mean and standard deviation. So now let me just run this. So here if you notice your first 11 rows is NaN, that is not a number. Now this is because we have calculated all the averages of these 11 and given over here. And similarly you can do the same for the next ones. Next, if you just scroll a little bit, you'll see it's a long data set and you have the same result for standard deviation as well. So it's the same procedure guys, average has been calculated and then just given out. So here you must be having a question why only 11 values are NaN. So over here we have just given a window of 12. Let's say I've given a window at daily basis or you have data at a day level, then your window size would be 365. So here my data is at monthly levels, so the forecast will be on monthly only. Now similarly, if you have data at day level, then probably your window can be 365. So I hope you get the reason why I am giving the win as 12 and why we are calculating the mean and standard deviation. Then what we have done, we have simply plotted this rolling statistics bar. So here we have the original data which is just plotted by the color blue. Then we have the mean data. So here we have just plotted the mean for what we have just calculated above and then we have given the color red to it. Similarly, we have plotted the same for standard deviation and we have given a color black to it. After that, we have just given a legend, we have given a title to it, and now let me just run this code for it. So over here, you can see we have a plot somewhat like this. So guys, blue line is my original data. And as you can see, I have my mean in red and I have a rolling standard deviation in black color. So over here, you can conclude that your mean and even your standard deviation is not constant. So here your data is not stationary. So guys, this is my rolling statistics method, which is again a visual technique. So here we have already concluded that this is not a stationary data set. Now let me perform Dickey-Fuller test as well. So to perform Dickey Fuller test in Python, you have to import from statsmodel.tsa stat tools import adfuller. Now this is the function which has been provided in Dickey Fuller test. So here I have a function that is adfuller. I have passed the data set into it, which is the number of passengers, and then I have just given a lag, which is equals to AIC. Now AIC is basically Akai information criterion. Now what does this AIC mean? So AIC gives you the information about what you wanted in time series, the exact value to the actual value, and it analyzes from the difference between them. So don't just worry about this, guys. For now, just think about this as a metric and see what happens when we just run this Dickey Fuller test. So when we run this, we'll have values to test statistics. We have p-value, number of lags that has been used, and number of observations used. And then we have printed the values in a loop. So now let me just run this cell as well. So this for statement will basically print all the values. Now I have a state statistic value, a p-value, number of lags used, number of observation, and we have critical value at different percentages. So here your null hypothesis says that your p-value should be always less. So here we have a very large value that is 0.9. So this should be somewhat around 0.5. So that would be a great thing. Also, a critical value should also be more than the test statistic. So here we cannot reject the null hypothesis and we can say that data is not stationary. Then what we'll do, we'll estimate the trend. So here also with the results of Dickey Fuller, we got to know that the data is not stationary. Then what we'll do, we'll estimate the trend. So here what we have done, we have taken a log of the index data set. So index data set is nothing but the data set which has index as time or the data which has been set monthly wise. So here we have just taken a log and let me just run this for you. Now if you see here, numbers on your y-axis have changed because the scale itself has changed. Here we have taken the log, but here your trends remains the same, whereas the value of y has been changed. Next, let us calculate the moving average with the same window. But keep in mind, guys, that this time we'll be taking up with the log time series. So again, we'll be having window is equals to 12, that is nothing but the 12 months. And then we'll be just plotting the graph with the log time series. So here data is already in the logged form. So now let me just print it. So here you can conclude that mean is not stationary, but it is quite better than the previous one. But again, it is not stationary because it's moving with the time and this trend is again an upward trend. So we can say that the data is not stationary again. Next, what we'll do, we'll get the difference between the moving average and the actual number of passengers. So we have mean and the actual time series that we have. Now, why are we doing this? Now, the reason is that unless we perform all these transformations, we'll not get the time series as stationary. So now you must be having a question as to whether it's the standard way to make a time series stationary. No, it's not, guys, because it depends on your time series as in how you can make it stationary. Like sometimes you have to take log, sometimes you might want to take a square of it, sometimes cube roots. So it all depends on data what it holds. So here we're going to log scale. So we are going to take MA and then subtract both of them. So here we have the log scale and we have the moving average. And then we have just printed the head of it, that is the top 12 values. Then what we have done, we have just removed the NaN values. So that is done by just typing drop NA and in the brace you can write in place dot true and then just print the head of it. So now let me just run this. So here we have the month and we have the number of passengers. So here we have the numbers which is basically the difference. Then moving ahead, I have purposely put in actual code of this ADCF test. So ADCF is the augmented Dickey Fuller test. So above I have just applied a simple ADCF function. But this is the whole code, guys. So you have to perform this whenever you have to determine whether time series is stationary or not. So here I have defined a function which is test stationary and I have performed both the tests. I have determined rolling statistics as well as performed Dickey Fuller test. So over here I have used the window as 12 and then I have plot rolling statistics as well I have performed the Dickey Fuller test as well. So let me just run this and I'll just run the function as well. So now if you see, you have the original data as blue lines, then you have standard deviation in black line and you have rolling mean in red line. So here you can visually notice that there is no such trend, or you can say it is much better than what we used to see earlier. So here we have rolling standard deviation and we have rolling mean. Now let me see the ADCF results as well. So here if you notice, your p-value is relatively less. In early cases we used to have 0.9 something and over here you have p-value at 0.02. Now if you notice, your critical value and your test statistics value is almost equal, which basically helps you to determine whether your data is stationary or not. So I hope by now you got the idea between the Dickey Fuller test and the rolling statistics test as to how you can determine whether the data is stationary or not. Next, what I've done, I've calculated the weighted average of time series. Now, why I have done this? Because we need to see the trend that is present inside a time series. So that is why we have calculated the weighted average of time series. So now let me just run this and you'll get to know why I'm talking about this. So as you can see here, as the time series is progressive, the average is also progressing towards the higher side. So here your trend is upward and keeps on increasing with respect to time. Moving ahead, let's see another transformation where we have a log scale and then we'll subtract the weighted average from it. So in a previous scenario, we have subtracted simple mean, but in this we'll be using weighted mean and then we'll check for stationarity. So here we have just subtracted them and then passed the variable in the test stationarity function that we have just defined it over here. So over here it will go through both of the tests and then it will display the results. So over here I'll just run the cell. So over here you can notice that your standard deviation is quite flat. It is not moving here and there. And in fact, you can also say that this doesn't have any trend. Also, if you notice the rolling mean, it is quite better than the previous one. Now let me just see the results of ADCF test as well. So over here you have a very less value of P, that is P is equals to 0.005. So your TS is again stationary, which means that your time series is again stationary. So here you can use both this transformation to check whether your data is stationary or not. So now we know that our data is stationary. Now what we'll do, we'll shift the values into time series so that we can use it in the forecasting. So what we have done earlier, we have subtracted the value of mean from the actual value. Now what we'll do, we'll use the function called as shift to shift all of those values. So here let me just run this plot. So this is how the plot looks like. Now here we have taken a lag of 1. So here we have just shift the values by 1, or you can say difference your time series once. So guys, if you remember, I talked about the ARIMA model. So ARIMA model has three models in it. That is the AR model, which stands for AutoRegressive. Then we have MA model, that is for moving average, and I is for the integration. So ARIMA model basically takes three parameters. And D there stands for the integration part, or you can say how many times you have differentiated a time series. So here your value becomes 1 now. Next, what I have done, I have simply dropped the NaN values. So here, if you just run this code, you'll see that output is quite flat. So here your null hypothesis or the augmented Dickey-Fuller test, wherein we'll take the null hypothesis, is rejected, and hence we can say that your time series is stationary now. So here you can say that you again have blue as the original data, you have red as your rolling mean, and you have black as your standard deviation. So visually also we see that there is no trend present and it's quite flat. So here we can say that your time series is stationary. Now let us see the components of time series. So here you first need to import from statsmodel.tsa.seasonal, import seasonal decompose. So here your seasonal decompose segregates three components, that is trend, seasonal and residual. So here what we have done, we have simply plotted these graphs and let us see how all these graphs looks like. So let me just run this. So this is how your output look like. This is my original data, which we saw that there was a trend. So this is my trend line. So this is going upward, in which you can say it's quite linear in nature. Along with that, we have seasonality also present in high scale. So we have a seasonality graph over here. And then we have the residuals as well. So residuals are nothing, guys, the irregularities that is present in your data. So they do not have any shape, any size, and you cannot find out what is going to happen next. So it's quite irregular in nature. Now what we're going to do, we'll check the noise if it's stationary or not. So over here we take the residual and we'll save it in a variable that is decomposed log data. And again I'll just pass it to the same function that we have just created above, which is test stationary, and inside this test stationary function we have two tests, that is rolling statistics and ADCF test. So now let me just run this cell and this is how your graph looks like. So looking at the output visually, you can say that this is not stationary. That is why we have to have your moving average parameter in place so that it smoothens it out to predict what will happen next. Now we know the value of D. But how can you know the value of P and Q? That is the value of autoregressive lags and the value of moving average. So here, as I told you guys, we need to plot ACF graph and PACF graph. So in order to calculate the values of P, we need to plot PACF graph, and in order to calculate the value of Q, we need to calculate ACF graph. So ACF basically refers to your autocorrelation graph and your PACF stands for partial autocorrelation graph. So in Python, we first need to import these two graphs, that is from statsmodel.tsa.stattools, import ACF and PACF. Then using this function ACF and PACF, we are just passing a data set and we have preferred a method that is OLS. So there are various methods, but we usually prefer OLS. So OLS is ordinary least square method. Then what we have done, we have simply plot ACF graph and we have plotted the PACF graph. So now let me just run this and let's determine how you can calculate P value and Q value. So guys, this is my autocorrelation graph and this is my partial autocorrelation graph. Now in order to calculate the P and Q values, you need to check that what is the value where the graph cuts off or you can say drops to zero for the first time. So if you look closely, it touches the confidence level over here. So here if you see your P value is almost around 2. And similarly, if you look at this graph, you'll see that it cuts it over here or it drops to 0 over here. And then the value of Q also becomes 2. So this is how you can calculate the value of P and Q using PACF graph and ACF graph. Next, we have the value of P, we have the value of Q, and we have the value of D. So what we can do, we can simply substitute these values in the ARIMA model. So here what I've done, I first imported the model ARIMA, and then using the function ARIMA, I have the order listed over here. So I have P value as 2, I have differenced it once, so my D value becomes 1, and my Q value is again 2. So here I have just plotted the graph and then calculated the RSS, which is the residual sum of squares. So here let me just run this graph. So here you can see the residual sum of squares is quite good, that is 1.02. So here you have plotted the values of P, Q and D as 2, 2 and 1. Now you can also play around with these P and Q parameters. Now let's say I want to change the parameters to 2, 1, 0. So if I do that, let me just run this again. So here if you see, once I have just changed the value to 210, my RSS score has been increased. So greater the RSS, the better it is for you. Now let me again change it to 012. Now in that case also my RSS has been increased to 1.4. So here you need to take care of the RSS part. So the greater the RSS, the better it is for you. So here we'll just revert back to 212, wherein we have the value of P as 2, Q as 2, and we have taken only one difference, so the value would be 1. Now let's take the moving average model in consideration. So here a P value is 0. Now for our model you have to do 210. Next for AR model what you can do, you have to do 210, wherein you have the value of Q as 0. So here I have 210 and let me just run it for you. So here you can see that your RSS has again reached 1.5. Now we have seen that with respect to AR, that is your autoregressive part, your RSS is 1.5. Now if I again go to MA wherein I have the values as 012, the RSS score is 1.4. So here we conclude that with respect to autoregressive part, we have the RSS as 1.5. With respect to moving average, we have the RSS is 1.4. And if we combine both of them and make ARIMA out of it, that is this part, that is 212, we have very less RSS. So let me just run this as well. So here when I substitute the values as 212, that is P and Q value is equals to 2 and D we have taken as 1. So here your ARIMA model gives you RSS of 1.02, which is quite good. Next, what we'll do, let's fit them in a combined model that is ARIMA. So here we have seen that with respect to AR, we have RSS as 1.5. With respect to MA, that is moving average, we have RSS as 1.4. And when we apply the combined model that is ARIMA, the RSS or you can say the residual sum of square is dropped to 1.02. So here let's do some fitting on the time series on what data we have. So here we have just converted the fitted values into a series format and then we have just printed the head of it. So now let me just run this. So over here we have the month as well as the predictions over here. Next, what we'll do, we'll find it the cumulative sum and then we're going to have the predictions done for the fitted values. So now to calculate the cumulative sum, we have the function called as sum and then again we have just printed the head. So this is my result. And finally, we're going to have the predictions done for the fitted values. And then we have just printed the head of it. So now let me just run this. Next, we also keep in mind that after performing these transformations, we also need the explanation of the whole data so that it comes back to the original form from where we have just started using it. So in order to know the values in that form, you need to take the exponent of it. So these are the three steps which are very important for data transformation. So you'll be finding cumulative sum, we'll do the predictions and we'll also calculate the exponent of it so as to get your data in your original format. Now after that, we just plot the actual values to how our model has fitted. So now let me just run this. So you can see that the orange line is basically the model that we have fitted. And here you can see that only the magnitude is varying, whereas the shape has been properly captured by the ARIMA model. Now, how we can do predictions, guys? Now, there is a function in Python that is predict. Now, before predicting the values, let me first see in my data that how many rows are there in my data set. So this is my data set name. So now let me just run this. So here we have the data set from 1949. We have the number of passengers. It will go on till 1960, and we have 144 rows into one column. So here we got to know that we have 144 rows. So what if I want to predict it for next 10 years? So what will be my prediction? Now here you have to see that how many number of data points would you want. So let's say if you want to predict for 10 years, so the number of data points would be 120, that is 12 into 10. So here if you want to predict it for 10 years, you have 120. So using that plot.predict function, I can actually predict the future. So here using this function, I'll give the first index of the time series and then the number of data points you want the time series for. So I have 144 rows plus 120 because I want it for 10 years. So 144 plus 120 is equals to 264. So I'll write it over here. Now let me just comment this for now and let me just run it. So over here, if you can see, my blue is the forecasted value and this gray part is your confidence level. So now whatever happens or however you do the forecasting, this value will not exceed the confidence level. So this is how you can see that for the next 10 years, you have the prediction somewhat like this. So this is how you can do prediction. And if you don't want to see the graph, you can actually write in the data point. So here I want the prediction for 10 years. So I have just typed in the steps that is equals to 120 and you get the result in an array format. So that is how you can perform a lot of operations with this data and predict it for let's say 6 months, 12 months, next year, 10 years, and it's totally up to you guys. Whatever topics that I've covered, I hope these are clear to you. So now let me just go back to my presentation and let's see what all we are left with. So here we have just built a model wherein we have forecasted the demand for the next 10 years. So in our dataset, we have the date in the monthly basis and we have the number of passengers. So that's all for today, guys. Now let me just recap what all we have covered till now. So we have started off by discussing what exactly is time series, and we've also gone through the various components that are trend, seasonality, cyclic, and irregularity. Then we have understood what is stationarity and what are the different tests to check the stationarity of the data. Then we discussed one of the best models which is used in the time series analysis, that is the ARIMA model. So here we have understood that ARIMA model is a combination of three models, that is the AR model, which stands for auto-regression, we have MA for moving average, and ICE for the integration part. And then we have implemented all these things and we have forecasted the data for the next 10 years. So I hope you guys are clear with whatever concepts that I've taught in this session. So do you guys have any questions or any doubts with respect to any of the topics that I've discussed till now? Alright, so I don't see any doubts over here. Alright, no problem guys. This takes time. So just go home, just practice, just go through the code again, practice as much as you can. And in case you have any doubt or any error, you can always come back to me or you can simply ask me in my next session. I hope you guys found this session informative. Well, thank you so much. Bye bye.
I hope you have enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply them at the earliest. Do look out for more videos in our playlist and subscribe to Edureka channel to learn more. Happy learning!